Yield lines, special cases. This video will deal with square slabs, partially distributed loads with fixed end supports. Consider a square slab, fixed end on the four sides, and a load equal to Q times B squared. B, of course, is between 0 and A. First, we look at the axis of rotation. So at the four supports, we have the four axes of rotation, and the yield lines are between the crosses or the intersections, the intersections of the axis of rotation. So we have from this to there and on the other side, but we have also, because it's a fixed end support, bending moment or a plastic bending moment on top of the slab, which is on the four sides. So we have also there the yield lines. Consider now a section here through, then you see that the maximum or the unit deflection is delta in the middle and 0 at the end, and the angle of deflection is theta. For small angles, the tangent theta is equal to delta divided by A over 2. That's only valid for small angles, theta. And the delta 1 here is, of course, delta 1 divided by this length, which is there, is also the tangent of theta and is equal to delta divided by A over 2. So from this we get delta 1 by this expression, and the mean deflection of that portion, loaded portion, is of course the uniform deflection delta 1 plus this triangle. This height of the triangle is delta minus delta 1, and it's a triangle, so it's 1/3 of delta minus delta 1. Substituting for delta 1 gives you that the mean deflection of this loaded area is equal to this expression. So when this is 0 and this is delta. Now let's look at the work done by the external forces. It's the summation or the integral of the loads with their deflection. So in our case, it is the total load multiplied by delta M, and we have calculated in the previous slide delta M, which is this expression. The work done by the internal forces is the integral of the bending moments multiplied by the projection of the yield lines to the axis of rotation times the angle of rotation. So here in our case, we got this bending moment projected on this axis of rotation, which is the length is A, and the rotation angle is of course delta divided by A over 2. Now we got this once to this axis, one to this action, rotation x, and this. So we have that 4 times, which is this. But we also have the bending moment on top of the slab, and we have that 4 times, and the angle of rotation is delta divided by A over 2. So in total, we got 16 times M times delta. By making E equal to D, we find M, and M is equal to this expression. Now consider uniform loads on the slab. The slab is fully loaded. Then we take the limit of this expression of B going to A, and we find QA squared of over 48. Looking at the point load, then we can use the general formula of partially loaded. by making the total load equal to QB squared. So it's like there is a very small b here. And replacing this in this formula, you find this expression, and the limit, taking the limit for b going to 0 gives you p over 16. Now we can put it in another way, a more general way, by taking the overall equation of the bending moment for fixed end supports, the loads ratio, we take it as b over a, beta is b over a, meaning that when beta is 1, the slab is fully loaded, and when beta is small or 0, it's a point load. Then the bending moment in function of beta can be written as this expression. And now you see here Q8 squared over 48, which is the maximum bending moment when the slab is fully loaded. And what is left is a coefficient K, coefficient as a function of beta, which is beta squared times 3 minus 2 beta. Now it's easy when you have it's easy to calculate the maximum bending moments because it's just the maximum that you expect from fully loaded slabs, which is Qa squared over 48, because the ends are fixed end supports, times the coefficient K beta. You will notice that this coefficient, of course, is exactly the same as for simply supported slabs. But for simply supported slabs, this is 24, and now for fixed end support is 48, but the coefficient is the same.